Okay, we can begin.
Yes.
Yeah, okay. So welcome everybody to the last talk of today. We have Dr. Rajesh Mondal from NIT Calicut, and he's going to talk about 21 centimeter cosmology.
Yes. Can you see my screen?
Yes,
Hello.
yes, we
Okay.
can.
So I'll be talking about the 21 centimeter cosmology. The plan of the talk is this. So we'll first discuss about the what is this 21 centimeter cosmology, then the physics related to that, and then for modeling we use simulation. I'll talk about something like particular type of simulation, that is semi-numerical simulation we use, and then how we detect, how we observe that signal. There are two ways. One is the global signal we observe, and there is another way is the fluctuation at various scale that also we observe. Then finally, I'll talk about the dark ages project that we have been doing last few years, and then finally the synergies that has been done in our group. Okay. So, what is this 21 centimeter cosmology? You see, this is the constituent of the universe at present. You see, 68% of the universe is dark energy, right? And 26% of the universe is dark matter, and only 5% of the universe is the visible matter that we see. And out of this visible matter, 75% of the matter is hydrogen, and 25% is helium by mass. So most of the matter we see, the higher element, higher than helium, is negligible, and in number, almost 95% of the universe is made up of hydrogen atom, hydrogen basically. So hydrogen is the most abundant element, so that is why we are interested in observing hydrogen. Now let us understand how this hydrogen evolved in the history of the universe. So as you know, after the Big Bang, universe expanded very rapidly, and uh, and it cooled. And when the universe size of the universe is roughly of the order of the 1,000th of today's size, then what happens is that the temperature of the universe is no longer valid to for this thermal coupling of matter and radiation. So what happened is that radiation decoupled from the matter, and that radiation we see as cosmic microwave background radiation, and which fills the universe. And the temperature of this cosmic microwave background radiation is today 2.73 degree Kelvin. Then after that, and this epoch is also sometimes called the epoch of recombination. And after that, what happens is that the universe remains neutral for uh, thousands of years, and the fluctuation in that period is linearly grow. And since the fluctuation is very small, of the order of, so when it started, it is of the order of 10 to the minus 5, and so that time it is not possible. There is no source you can have, and that period is called the dark ages. Dark because there are no sources, and only the fluctuation that was there in the CMB, that was basically amplified through gravitational instability. After that, what happened is that density field become non-linear, and at some point, this non-linear density field have enough density quanta that can produce the first sources of light, and that first sources of light, ignition of these first sources of light is called the cosmic dawn. Then these sources emit highly energetic X-ray UV radiation, and those radiation you see can ionize the hydrogen, neutral hydrogen present in the intergalactic medium, and that process called the reionization. And it is the time is called the epoch of reionization. And when I say reionization, I refer the reionization of the hydrogen. Okay. After that, what happens is the universe become fully ionized, and the universe we live currently is ionized universe. Most part of the universe is ionized. How do we know that? We know from various observations, and one of the observation is Lyman alpha observation. So what we see very high redshift quasar or very high redshift white sources, and light from those. For example, if we are observing this light from those sources, will propagate through this intergalactic medium, and from this measurement of this light, we can see the constituent of that line of sight matter. And from that thing, we can predict that the ionization fraction of the universe, sorry, the neutral fraction of the universe is of the order of 10 to the power minus 4. Means only one in 100,000 particle, a hydrogen atom basically, is neutral, means that universe is fully ionized. And we see that mostly this Lyman alpha peak, that is this 1216 angstrom peak, basically, we observe. Now, you see, we have been observing and we have observed the CMB for quite many years. And this is the CMB spectrum, that is the black body spectrum you see. And we have measured this so accurately. You see, this error bar in this spectrum is 400 times the sigma. That is the 400 sigma error bar. Means you have the best measurement of the black body spectrum for this CMB. And we also observe the fluctuation that you can see here itself. That you can see here. And also, we can observe the fluctuation, the large scale structure of the universe here. All right. My sound is clear. Means I cannot hear you or see you, so that is why I am just asking. Hello.
Yes, the voice is clear, but we can.
Okay, fine. So
now we can see the slide.
Fine. Now the question is how the small fluctuation that was there very early time gives rise to the fluctuation that we see at the present day. And this is the galaxy redshift survey, 2DF galaxy redshift survey. These are all our points are galaxy basically. Each point is a galaxy. So this is the fundamental question, and to know this thing, we can use hydrogen to trace the history of the universe. That is the plan. Okay. Now, how we can observe this? How we can observe this hydrogen? So one of the observations I just told you, that is the Lyman alpha observation, but that is very high energy observation, and for that we require UV radiation to see those observations. But at everywhere in the universe, we don't have these high energy photons, right? It is only we can see from very bright sources or star forming region. But there is another possibilities in the hydrogen atom, that is this thin film 21 centimeter radiation. So what is it that? So we know it's a hydrogen, neutral hydrogen in the ground state has this proton and electron, and they when they spin, they have this magnetic moment, and this spin magnetic moment basically can align parallelly or anti-parallelly. And this two alignment has a tiny energy difference, that is this 5.9 into 10⁻⁶ electron volt, very tiny. And that difference can give rise to this radiation, that is this 21 centimeter. That wavelength of that radiation is 21 centimeter. That is why this radiation is called the 21 centimeter radiation. And the frequency corresponds to that is 1420 megahertz in the radio. So it's in the radio. Okay. Now, how we quantify this radiation? To quantify this radiation, we use a temperature that is called the spin temperature. So the spin temperature is defined like this ratio of the higher energy state, that is this, to the lower energy state, and that is related by this Boltzmann factor, and that is this. 3 is the spin degeneracy, and this exponential the energy by K that we define as T star, and this Ts is the spin temperature. So that spin temperature determines the spin configuration, means whether it will be in the high energy state or the low energy state. And this is one of the promising probe, because we don't need any source set, right? If you excite one hydrogen atom to this high energy state, there is a possibility, although it is very small, there is a possibility that can basically gives rise to this 21 centimeter signal. And I told you, in the universe we have mostly hydrogen, so and universe is very vast, so we can observe this 21 centimeter signal, and it has been observed for various sources. So that is the I'm talking about. Now, how we observe? So in this figure, you can see we are at the center, and we are looking into various redshifts. That redshift corresponds to defined distances, basically. And this is the CMB. That is that one. This is the CMB. Okay, and these are the surveys that going on, and various distances and various redshift. So what we see? So we see the 21 centimeter signal we can observe from any distances, because everywhere we have hydrogen. But the background is CMB. So CMB is the background. You see CMB is here. And this 21, this hydrogen atom can basically absorb this photon. So because CMB is a Planck spectrum, it can emit at all the frequency. You see, it can emit signal at all the frequency. So hydrogen atom can, in principle, absorb this 21 centimeter, the particular frequency also. It can absorb and emit, right? If it is in the ground state, it can absorb. If it is in the high energy state, it can emit. Okay. Now that is the case. So what we see is something called the intensity. So since it is in the Rayleigh limit, means the wavelength is very large, so we can associate a temperature as in it to be the black body. So the intensity that we observe, we associate a temperature, and we talk the radiation in terms of this temperature, that is called the brightness temperature. Okay, and as I told you, we observe this intensity or the temperature in the background of this CMB. So what we exactly observe? We observe the spin temperature minus the CMB temperature. If the spin, so if suppose the spin temperature, that means this spin temperature is exactly same as the CMB temperature, we get a zero signal. Okay. Suppose the hydrogen atom is in equilibrium with the CMB, then we will not see any signal. We will only see signal if the spin temperature is more than the CMB temperature, that is the emission, or the spin temperature is below the CMB temperature, that means it is in the absorption. Okay, so that is the quantity that we observe. That is called the brightness temperature. Now, what this brightness temperature, what this spin temperature is, how we calculate this spin temperature? What are the factors that determines the spin temperature? So there are three processes mainly that determine this spin temperature, and this spin temperature will basically tell us what is the brightness temperature. So as I told you, the first process is the CMB. So the CMB photons can interact with the hydrogen atom. Okay, and when they are interacting, so basically this is Thomson scattering. When they are interacting, what will happen is that the spin temperature will go to the CMB temperature. Means they will be in equilibrium. Means the CMB temperature and the CMB temperature will be in equilibrium. So then, in that case, we have zero signal. So this process are not desirable, basically. So what is the next process? Next process is the collision. So in the collision process, when the hydrogen atom or hydrogen some small fraction of electron or some other when they collide, they can lead this spin temperature to the kinetic temperature of the gas or the gas temperature. And in that case, this case is useful because the gas temperature, in the universe, the gas cool faster than the radiation. Gas cool adiabatically faster than the CMB. So in that case, what will happen is that Ts will be less compared to the CMB, and we will get a negative signal, absorption signal. That I'll tell you in the next slide. And the final process is the Augusten field effect. That was basically a subtle effect that was discovered by this atomic physicist. So what is this process is called? Because you see, the hydrogen atom can absorb and emit light and alpha photon. And when it is absorbing, it will go from n equal to 1 to n equal to 2. And when it will emit the light and alpha photon, it will come down to the ground state. But while coming down to the ground state, this spin can mix, means it can end up. So suppose it is going from this 0, it can end up in the one state. So that is how this spin state can mix together. Okay. So what will happen is that the main crux of the whole thing is, in this process is only possible when there is line of a photon, means when there is a star galaxy in the universe, high energy sources. So during and when there are sources, the spin temperature will lead to the gas temperature. Okay, again it will be negative. It will be negative. That we will see in the next slide. So now before that, not only we see the signal will be redshifted because the universe is expanding. Suppose the signal was emitted at this frequency at some redshift z. By the time it reaches us, it will be redshifted to a longer wavelength. That will be this 1 plus z. Okay, that is because the universe is expanding. So we don't observe, most of the time we don't observe 21 centimeter signal. We observe a higher wavelength, that is depending upon the which redshift we are seeing. Okay, and the frequency corresponds to that observed wavelength will also change by this factor. Okay, so this is called the redshift, and this redshift is when I'm talking about redshift, the redshift not only consider the expansion of the universe, but also the peculiar velocities of the object. Suppose it is when it is emitting, not only expanding due to the cosmological expansion, if suppose it has some extra peculiar velocity, that will also be counted in this jet. Okay, so that is this case. Now comes to the global signal. Global means the mean signal. Mean signal as a function of frequency. So as you can see, so this is suppose. So this is frequency 1420 is the frequency at present. So as we go higher and higher redshift, you see the frequency is also decreasing by this factor. Okay, according to this formula. Okay. Now first let us understand what happens at the earliest. So at the earliest, what happens is that the CMB, the radiation, and everything is in thermal equilibrium. Okay, so you see everything is in zero. Okay. Now what happened is that as I told you, the gas temperature fall faster than the CMB temperature due to this adiabatic cooling. So gas temperature will fall faster than the CMB temperature, and you see in this time the universe was very dense, and the collisional process is the leading process. Collisional process take the lead. So that is why the split temperature is below the CME temperature. So that is why we see a negative signal here. Okay, you see there is this negative signal, and this signal, so the signal you see is the brightness temperature that I was talking about in terms of in the realization speed. Okay. Now what happens is that as the universe is expanding, at some point around this time when the redshift or the age, the frequency is around this 15 or 20, 15 megahertz, what happens is that this collisional process is no longer valid. You see this process, as the universe is expanding, this collisional process is no longer effective. So what happens is that this process, CMB will take over. Okay, so that is why the brightness temperature again goes to the CMB, and then we have a negative signal here. And then the signal goes to zero here. Okay. Now after that, what happens? After that, the third process takes place, that is the solution field effect. So first stars and galaxy form, and they will emit X-ray UV radiation, and that radiation basically it gives rise to this effect, and thus again the spin temperature will goes to the gas temperature, and again we have a negative signal. You see, we have a negative signal here. But not only we have the gas temperature is decreasing, but at some point what will happen is the gas itself will be heated by this X-ray radiation, because X-ray is very efficient in heating. So gas itself is heating, so it is following the gas, but the gas itself is heating, and the gas temperature is more than the CME temperature here. It will cause the CME temperature, and then we can see the signal in positive. So you see this signal is the positive signal that we see, and that positive signal we can see during the reionization. And this time is called the cosmic dawn or the heating epoch. Okay, and at the end of this thing, all the hydrogen is ionized, and then we see the reionization ends. So, and the signal goes to zero again. Okay, so that is the full story of this global signal. Now, there was this recent observation, not recent, in 2018, this AGS detected one of the signal. Okay, during this frequency 10 to no, so during this rate sheet 10 to 25. Okay, and and there has been hundreds of paper has been written to explain this this 21 centimeter signal during this time. And we also used this observation, although that observation was disputed by another experiment that is in India, that is called the SEARCH. And but the signal itself produces a lot of new physics and new speculation whether it is possible or not. And we also took that signal and generated various many more signal around that allowed range. And we do what we do basically, that I'll explain in a later slide. But that is, these are the some all possible global signal within the allowed range basically. So what we do with this thing, that I'll tell you in a few slides. And what else we can do? We can observe not only the mean signal but also the fluctuation. So fluctuation is the, as I told you, we have the observer here, and this is the CMB, and these are hydrogen cloud. You can say hydrogen, and they are interacting with the CM. And these three out of these three processes, some of them can be dominated. So what we see is kind of, so our line of sight axis is the frequency axis that we have already seen. Not only that thing, the sky plane, that is the theta x and theta y, also we can observe. Okay, so there is the theta x and theta y. So we can observe a 3D volume. Okay, the line of sight axis is the frequency axis. If we change the frequency, we will see a different distance. Okay, if we change the different frequency, we'll see a different distance. And that is how we can observe the 3D volume using this 21 centimeter signal. So resonance line and the redshift. Okay. Now there are these signals we observe using different type of telescope. These are called interferometer. The signal that that AGS detected was global signal. Okay, so these are monopole antenna, or basically a different type of instrument than the interferometer. So interferometer, what it does, it basically correlates signal at two antennas. Okay, and gives you the signal. Okay, so interferometer, that the signal that we observe is basically gives you the fluctuation in the signal. And if you change the frequency, you will observe different slices of the image. And that is how we observe 3D volume. And there are some, these are some names. GMRT is in India, near Pune. And Hera, this is called Nenufar, NWA. But I worked a few years back with this LOFAR instrument that is in Netherlands. That is a European project. And what we did, we observed that signal at redshift. Before that, that I'll tell you. So, so this I'll focus on this result from this telescope in a few slides. Okay, but the challenge, there are challenges. What are the challenges? The main challenges is the phone count. So what are the four counts? You see, this is the right hand side figure shows you the synchrotron radiation, the diffuse synchrotron radiation observed by Haslam. So what you see here, this is our own galaxy, and our own galaxy produces high level of radio emission, and which is basically 4 to 5 order of the magnitude than the signal that we trying to observe. Okay, so that is the problem. We have to remove this phone down to see the actual signal, and that is very challenging. And not only that, there are extragalactic point sources. So you see these small sources, these are extragalactic point sources, and they are also very bright. Okay, and removing these two is the biggest challenge that we face currently. Okay, we have instrument, but the sky itself is crowded with this radio emission, so that we have to remove. So for that reason, we are building another next generation telescope that is called the square kilometer array. That will be order of magnitude more sensitive than the current telescope that we have. Okay, and we are hoping that this instrument at least can do the sciences that we are trying to do for last couple of decades. And this is an international project. I can tell you more, but there is a time constant, so I'll go into that things that we do. So what we do is we first want to see what type of signal we are expecting. So for that, we need to model the signal. And for modeling, we use simulation. Why simulation? Because the physics is very complicated. The field itself, the underlying field itself, very highly non-linear, and the astrophysics I'll be talking about is also very complex. The star formation and all these things are very complex. So the scale I am talking, and the scale involved is very large. And scale I am talking about is from the smallest scale we need to resolve is of the order of 0.1 parsec to 10 kiloparsec. These are the scale for galaxy I am talking about. So galaxy is the sources that produces this radiation. Then we have to model the intergalactic medium that is of the order of 10 kiloparsec to 1 megaparsec in between distance, rough distance between two galaxies. Then next thing is the radiation. If the radiation is highly energetic, that can go even further, even up to hundreds of megaparsec it can go. It can ionize, so it has footprint. So for the X-ray and gamma ray, will have footprint up to hundreds of megaparsec. Okay, so the dynamic range is very large, and the radiation itself also it's not an easy task. Means you have to see this ray tracing basically every time you have to see whether it is ionizing or not. That is a very computationally expensive job. Okay, and the star formation itself also, how a different type of star is produced, how they will radiate, and their defined physics is very complicated. And the process itself, I told you, the radiative transfer process also is very complicated. So due to these reasons, we cannot do anything analytically. So we need to go, we have to use the numerical simulation to solve for the expected signal. So what type of simulation we do? First thing we do, so before that, how do we use the simulation? So we, as you know, we use simulation as a laboratory. So to acquire physical understanding and intuition, and predict the observable, that is the most time we do, and develop statistical tool based on those simulated things, and also use those model for fitting the data. Once you observe something, we use those model for model fitting and parameter estimation. And these things are very common in any astronomical data analysis. So first step is to generate the density, underlying density fluctuation. So as I told you, the underlying density is determined by the dark matter, because dark matter is the most dominant component in the universe. So what we do, we use a dark matter simulation. That is this a particle mesh n-body simulation. And what it does, it solves the dynamical equation in expanding background using particles, but the potential is calculated on a mesh. So that is why it's called the particle mesh simulation. And this is a time-lapse simulation. So we start at very early time when the universe was very smooth and let it evolve. I'm not showing you the equation, but you see that this gravitational instability means the higher dense region will become more and more higher dense, and this under dense region is becoming more and more under dense. So that is how structure in the universe form, and thus we can very most accurately do using simulation. And the next part is finding the dark matter halos or the halos. Okay, so for finding, so why we need halos? Because the halos are every galaxy resides in a halo. So halos are the host for the galaxies or any sources. So once we have the density field, we find the dark matter halo in that density field using an algorithm called friends of friend algorithm. And there are some checks and balances. I'm not going into those things because of the time constant, but you can check whether everything is correct or not using various type of analytical calculation. And then final step is the complicated thing. As I told you, star formation, radiation transfer, these things are very complicated. So how to do? We don't do those things. Because and these complicated. If we use those complicated simulations, they exist. But if we use those complicated simulations, what happens is that it will take a lot of time, and we cannot generate many simulations that is required for parameter estimation. So what we do instead, we take some assumption and we use an excursion set formalism. What is that excursion set formalism? I'll explain in a cartoon figure. So this is the density field, suppose we got, and then we find the halos, and then we place the galaxies. Okay. Up to this point, everything is same. As you see, the first 2 points are same. Next is a complicated thing. Next is how this properties of this star, means the galaxy's property or star property, and how they will emit and how this emission will propagate. This is the complicated part. So that part we simplify, assuming the radiation produce proportional to their masses. So more massive star, more massive galaxy will produce more radiation, and less massive. So that is the simple assumption that we do. And then we spherically, basically, let the radiation propagate. Okay. And spherically let the propagate and check whether one point is possible for that radiation to ionize or not. And that is there is this excursion set formalism. And then we find the this is called the ionization map. Okay. So the assumption I told you, the collapse halos holds the ionizing sources, and hydrogen traces the dark matter field. And once we have those assumptions, we can place the galaxies and calculate the ionization field using the excursion set formalism. And the code we use is called the RIAN Yuga. That is the code developed by many people in our group. And this is the simulation for hydrogen. So this is the hydrogen simulation. So as you can see, this is the fluctuation. The deep blue region is the high density region, light blue region is the low density region. And you see this transparent region is the ionized region. So as time evolves, what is happening is that this region of ionization is growing, means that ionization process is basically ionizing the surrounding intergalactic medium. Okay. And what happens is that at the end of this process, we only have neutral patches, small neutral patches, and most of the intergalactic medium will be ionized, depending upon the redshift, depending upon the distance we are talking about. Okay. So that is the whole process. And these are some snapshot. So this is the brightness temperature. Again, we talk in terms of brightness temperature. Although we see hydrogen, but we don't talk about hydrogen. We only see the brightness temperature or intensity in terms of brightness temperature. And these are some snapshots at defined redshift. So this is the highest redshift, and it is decreasing clockwise. Okay. Now, what we do with this, we find observable statistics. And the most common statistic is the spherically average power spectrum. What is this power spectrum? Is we break this density field into Fourier modes, and we calculate the amplitude square of this Fourier mode. That is basically will give you the power spectrum. And then if it's spherically average over this power spectrum, we get the spherically average power spectrum. And what it tells you the variance in Fourier space at defined scale. So these are some power spectrum. So this is called the dimensionless power spectrum. To basically this is kq pk by 2 pi squared. So this is only pk, and if you multiply with kq and divide by 2 pi squared, that will give you the dimensionless power spectrum as a function of wave number. And this wave number is 2 pi by the length scale. Okay. So higher k value means smaller length scales, and larger k value means the smaller k value in the large scale. Okay. So you see, so these are the 10 centimeter power spectrum at different redshift or equivalently at different ionization fraction. Okay. So what it tells what you can do with this thing, that I'll tell you in the next slide. So I was talking about Loeffler observation. So then in 2020, Loeffler observed these green points. Okay, so these are the power spectrum upper limit. And the models I've been showing for the global signal, the same model will give you the power spectrum, and that has been plotted here. All these lines are different models. Okay, there are thousands of models that is there. So how you can do these things in. So although it's a old paper, I'm showing you 2020, but the philosophy, the framework is same. Okay. So what we do, we have observation and we have models, and these are some latest result. Okay. For example, Hera and then LOFAR, and this is the LOFAR one, and the MW we also have. There are various type of observations that we do. So what do we do with these observations? So we constrain the astrophysics and cosmology. How? Basically, we have the major power spectrum, and we compare this major power spectrum with a large set of model. Okay, that I showed you using the Bayesian inference approach. Okay, using basically the MCMC approach. Okay, and as I told you, this type of analysis was used for in with great success with CND. CND people also have been doing this exercise for quite a few decades. And then I told you we need many models. So for that thing, we need a fast simulation. That is why we use a fast simulation with assumption. Not only that, we use also the machine learning techniques to make it even faster. We use emulator and all these things for that purpose. And these are the constant on our astrophysical parameters. I will not go into the details, but you see we have this model, we have this observation, we feed the model using NCNC, and we get the constant on defined parameter. Since this observation was very not very accurate, because these are basically a limit, upper limit, so that is why these constants are also not very accurate. Accurate in the sense that the error bars are very large. Okay. As the observation is getting better and better, this error bars are shrinking right now. Okay, and Hera and other telescope have produced better result. Okay, so the technique is same that I am talking about. Now there are other complications. I will not go into the details. For example, I'll just tell you the idea. For example, when you observe a large volume, what happens is that the frequency along the frequency axis, the signal that changes, meaning the statistics of the signal changes. Hello. So when that time when we talk, yes,
we have 5 minutes left.
Okay. So I'll skip these things here. Okay, fine. So the idea I just told you. So I'll go into the dark ages basically. Then I'll conclude. The same thing we can do it for dark ages. But for dark ages, as I told you, there are no sources of light. So we have a pure cosmological signal, just like the CN. So what is the beauty of that thing is that we can constant the cosmological parameter. Not only we cannot constant the astrophysical parameter, but we can constant the cosmological parameter in 3 dimensions, unlike CND. And we don't need to deal with the complex nonlinearity because things are already linear. And why we are doing this thing? Because of geopolitics, because there is a renewed interest to go to the moon and space. So there are many. I can give you some examples. For example, these are some examples proposed experiment that people are trying to send to the space or the moon. So that is why we are studying this dark ages. And we again modeling part I'll skip. So what is the result? So we showed that yes, it is possible to do science or the cosmology with the dark ages global signal. Although it is very difficult because we are talking about very small frequencies, but still we can do something with that thing. Similarly, for power spectrum also we can do. I'm not going into the details. But these are some power spectrum and these are some predictions that we made for different telescopic configurations. Okay, and these are the constant that can be achieved using. So these are for Planck and these are for different global signal and these are for power spectrum configuration that we observe, that we assumed basically. Okay, so compared to CM, you can see we can do better if we observe it for long time and defined configuration. So given that you can do synergies with, for example, JWST and other telescope, because they can detect various sources in details. So nature of the dark matter and early Galaxian rearrangement and UV luminosity function. So these telescope, this JWST telescope, can detect the sources in details, whereas we can detect the large scale picture of the universe. So we can complement each other and do science with those signals. So I'll conclude. So as I told you, quantum signal is a very promising form of the early universe, and it can uncover various mysteries of the universe. For example, what type of first luminous sources was there in the universe, how the reionization process and the large scale structure of the universe, and various other things related to the high redshift universe. And observation of the dark ages, cosmic dawn, and epoch of dilation has been identified as key science driver and priority for various telescopes. I have shown many telescopes, and SK is one of them that will observe the epoch in detail. But there are challenges. For example, 4-count I talked about, but there are other challenges. There are instrumental challenges, that is calibration, and then what is the primary beam itself of the telescope is very difficult to model. And there is radio frequency interference and other things are there. But what I can say finally is that this is a relatively new field and very active field. You can see the archive, how many papers have been written every day. You'll find something. Okay. And there have been observations. It's not like only theoretical things are going on. People have been trying their best to observe. For example, I told AJ, Sarah, Slofa, NWA, Hera, and all these things. They have moved the observation also forward quite a lot. And we have been doing modeling and simulation things. That is also developing and also developed quite a lot over the years. And right now we can put statistical constraint on various astrophysical parameters given this observation from the first generation telescope. But as I told you, there is not yet to be done. Okay, I'll not take question.